HighBridge, a division of Recorded Books, presents The Secret Science of Baby, the surprising physics of creating a human from conception to birth and beyond, by Michael Banks, read by Jonathan Cowley. Introduction. If you have started listening to this book, there is a good chance you either have children or have one on the way. Or perhaps you may just be curious about how physics can possibly have anything to do with babies. If you are expecting, then congratulations! Your life will now, or soon, change forever. Interrupted nights, never going out in the evening, going to the restroom with an audience, pushing your screaming child in the buggy in the rain, desperate for him or her to sleep. Again, many congratulations. After blood, sweat and plenty of tears, childbirth is a moment of pure joy and something you will most probably only experience once or twice in your life. It is a major milestone, especially for grandparents who have been waiting years, if not decades, for the moment they can finally put that homemade knitted hat on their grandchild for the first time. Pregnancy is also a time when parents are bombarded with information. What to expect, what not to do, and how that little embryo is developing week to week, including the bizarre use of different fruits as a unit of length. Rather than use parents and carers throughout the book, I only use the term parents for ease of readability. There may also be instances where I use mother or father, but of course recognize that there are same-sex couples who may use different terms. If you are after any of that, then, alas, you may be better served elsewhere. This book will not tell you what to eat during pregnancy or describe the techniques to get your baby to sleep through the night, nor will it advise you how to raise a perfect violin-playing mandarin-speaking toddler. Research into the latest child psychology is absent here, having been well trodden in countless other books. Instead, The Secret Science of Baby will explain, from a physics perspective, how or why things happen. For example, how can cells in the uterus contract in unison to expel a 4-kilogram, 8+ pound baby? What is it about an infant's cry that solicits parents' attention so effectively? How does a newborn effortlessly extract milk from the breast? The book will also shine a light on the latest science behind many aspects of conception, pregnancy, and baby development, while not shying away from highlighting the limitations of such work and what remains to be discovered. The book will detail how such research has generated answers, new insights, and yes, more questions. The Secret Science of Baby also highlights how technological development over many decades has reflected the true spirit of curiosity-driven physics research. We'll explore techniques developed by physicists, engineers, and mathematicians to get a better understanding of what the human body, particularly in baby form, can do. When people think about physics, the first thing that likely comes to mind is the universe, quantum mechanics, or the hunt for fundamental particles of nature. Yet physics is a subject that touches on so many more different areas, and many of the tools that physicists have built, be it machines like magnetic resonance imaging, MRI, or theoretical models, have often found uses beyond those directly intended. Albert Einstein's theory of general relativity in the early 20th century, for example, paved the way decades later for global positioning systems that allow us to know where we are anywhere on the globe with a precision of a few meters or a few yards, while the advent of quantum mechanics in the 1920s promises unbreakable communication as well as computational ability far more powerful than their classical counterparts. And yes, even when it comes to conception, pregnancy, and babies, there are many insights that physics can provide, from examining how infants draw their first breath and understanding how gases diffuse through the placenta to touching upon the science of how infants acquire language. While focusing on the physics, There may be times when I stray into other areas such as chemistry, mathematics, engineering, and even neuroscience. Indeed, the power of physics, as we will see, lies in its interdisciplinary nature. Yet, I hope to show that examining how things work, a perspective I did not come across when I was head-deep in parenting and pregnancy books as an expectant parent, might lead to a better appreciation of how it is possible to create another human and why and how our bodies and babies do what they do. After all, the infant universe is a special place. 1. The coitus experiment. It is fall 1991, and the Dutch physiologist Peck van Andel is attending a scientific meeting on medical technologies that is being held at the University of Groningen in the Netherlands. He enters the university and sits down in one of the nondescript lecture rooms, looking forward to the many presentations that will be given that day. Talk after talk passes by, but then one address piques Van Andel's interest. During it, the speaker plays a video showing the inner workings of the mouth and throat of a professional opera singer belting out, "Ah!" The black and white moving images of the vocal tract are incredibly clear and mesmerizing in detail, showing anatomically how the larynx of a talented singer produces such a rich sound. Working at the Groningen University Hospital at the time, Van Andel is awestruck by the beautiful body art images he is witnessing that day. During the rest of the conference, with the film still playing in Van Andel's mind, he begins to think, as any good scientist would, how he could employ the technique for his own research. He has an idea, yet this would not be his typical area of scientific expertise, and it would also require help from others. He first tries to persuade his wife, who refuses, but instead offers to speak to a friend, the organizational anthropologist Ida Sibelius. Intrigued and open-minded enough about the proposal, Sibelius, with her then-boyfriend, identified only as Jupe, agrees to meet Van Andel and colleagues at the hospital to discuss the experiment. In the spring of 1992, the pair travel the 3 hours by train from Amsterdam to Groningen. Following a briefing about the procedure, all parties are satisfied under a few caveats, such as scans are to be done in secret and the movies are only to be used for scientific purposes. The date of the scan is then set, October the 24th, 1992. As the months pass by and the day of the scan gets ever closer, Sibelius becomes more and more apprehensive while still wanting to go ahead. I was now worried that it was going to happen and what the consequences would be, noted Sibelius later. What would my colleagues, friends, and family say? Nevertheless, on that autumn day, the pair arrive at the hospital. They are greeted by the researchers and quickly ushered into a room. Given the tight space inside the machine, Van Andel's idea would be a challenge, but Sibelius and her partner are undeterred. They listen as the researchers go through the steps of the procedure, finish their coffee, take a quick stop at the restroom, and return before getting undressed. Then they lie beside each other on a small rectangular table, barely wide enough to fit them both, before being gently slid into the heart of the scanner. After some fumbling, a change of position, and some sniggering, the couple finally do it. The erection is fully visible, including the root. A voice booms over the intercom. Now lie down, be very still, and hold your breath during the scan. A few whirs of the machine take place, and then it is back to work. At the end of the session, the pair enter history as the first couple to have sex in an MRI machine. Well, officially anyway. The images that Van Andel witnessed during the conference on that day in 1991 were not like a typical movie produced with a video camera, but one made by a revolutionary new technology called magnetic resonance imaging, or MRI. The technique was developed in the 1970s and 1980s by several people, including the UK physicist Sir Peter Mansfield, who shared the 2003 Nobel Prize in Physiology or Medicine for his contributions together with the US chemist Paul Lauterbur. MRI machines are used to safely peer through the skin non-invasively to see what lies beneath. They were and still are huge pieces of equipment, mostly due to the need for a rather large magnet. The magnetic field employed by MRI scanners is typically around 1.5 Tesla, or about 30,000 times stronger than that produced by the Earth. During an MRI scan, the patient lies still inside the cylindrical bore of the magnet, the hollow space being only some 40 centimeters, 15.8 inches in diameter. Not pleasant for anyone with claustrophobia. Coils then scan the parts of the body that need medical attention. Some of the magnets in the first MRI machines were made of large solenoid-shaped copper coils so that when a current was driven through, it could produce a static magnetic field. Generating higher fields required more current, which became more expensive. Some modern MRI machines use superconducting magnets, which feature materials like niobium titanium that, when cooled to a certain low temperature, conduct electricity without resistance. This means they are more efficient and require less power, allowing them to generate much higher magnetic fields. The disadvantage is that they require liquid helium to cool them to temperatures of around minus 240 degrees Celsius, minus 400 degrees Fahrenheit. The role of the powerful magnet in an MRI machine is to pull on protons that are inside of us. Our bodies are about 60% water, which is comprised of 2 hydrogen atoms and 1 oxygen atom. The hydrogen atom's nucleus is a single positively charged proton, and when the magnetic field generated by the large magnet is switched on, this pulls the proton's spin to align along the same direction as the applied magnetic field, with a larger magnetic field resulting in better proton spin alignment. A way to visualize this is to imagine the Earth spinning on its axis, but with an arrow pointing out of it to represent the spin direction. When a magnetic field is applied along the north, the proton's spin will align along that direction. After the protons have been pulled into one direction, the MRI machine then directs radio waves at them. The radio waves are tuned to a specific frequency so that the protons absorb a certain amount of energy. This changes the direction of the proton's spin away from the direction of the magnetic field. When the radio waves are turned off, the protons relax, and the speed at which they do so depends on the chemical nature of the molecules in different parts of the body. This allows contrast to occur in different tissues in the body for clearer images. Picking up these relaxation signals via gradient coils located around the MRI machine enables 3D imaging to occur. Although MRI scanners are large due to the need to generate stable magnetic fields for image quality, the technique does not use ionizing radiation like X-rays, meaning 3D imaging is a powerful technique in medicine that can be used to spot cancerous tissue and study the brain. After seeing the MRI images of the opera singer's larynx, Van Andel's idea was to use the technique to create the first ever moving images of a couple having intercourse. For those who want to see it with their own eyes, a video of the MRI scans can be found here. www.youtube.com/watch?VAU3VY. This was not just an amusing or slightly kinky side project, but an attempt to see for the first time what happens internally during coitus. After all, for some 500 years, it was thought that the vagina was like a straight tunnel that the arrow-straight penis went in and out of. Perhaps the most famous example of this geometry is a circa 1493 drawing, The Copulation, by the Italian polymath and painter Leonardo da Vinci. Despite having little formal education, da Vinci kept extensive notebooks filled with his scientific theories, inventions, drawings, and designs. In engineering, he created once-thought impractical devices, from scuba gear to flying machines, and is particularly known in science for his work in anatomy, which includes thousands of pages of notes and beautiful anatomical drawings that fuse art with science. It features a man with a straight, erect penis that is inside a woman's vagina, diagonal in direction. Fast forward to the mid-20th century, and despite all sorts of efforts, including the use of artificial penises, scientists could not improve that description. Until, that is, Van Andel's work and the beautiful MRI images taken that day. After the couple's antics in the MRI machine, the team, including Sibelius, wrote up the findings and sent a scientific paper to Nature, one of the world's oldest and most prestigious scientific journals. It was quickly rejected, mostly due to one major flaw, a data point of one couple. Van Andel and colleagues went back to the drawing board to recruit more volunteers to try and obtain a more general idea about what was going on during coitus, while also improving the quality of the images. Getting new participants, however, turned out to be challenging. Crawling into an MRI scanner to have sex in such a small space, all the while being scanned by a huge magnetic field, rather unsurprisingly, did not appeal to many. Despite that, in 1996, the team persuaded 6 couples to give it a go. The team also had a new machine to play with, a Siemens Vision 1.5 Tesla MRI scanner that offered sharper images. Surely nothing could go wrong? Well, it did, and the couples had performance issues. Sibelius put her and her partner's first-time success down to their good relationship, while Van Andel thought it was more down to the pair's experience being street performers in their spare time. It turned out to be harder than it looks, with the lack of action usually pointing firmly toward the men rather than the women. Most thought it would be easy, Sibelius, who now works at the Vrije Universiteit Amsterdam, a public university in the Netherlands, explained to me. But they quickly realized that it takes real body awareness and a good relationship to do it in this way. 2 years later, a breakthrough came thanks to a new drug, Viagra. 2 couples were invited back to give it another go, and with help from 25 milligrams of the drug in the form of a blue tablet, the researchers finally got the images they wanted. When the researchers analyzed the results from all the scans, they saw something quite different from what Da Vinci had sketched more than 500 years ago. Instead of a straight penis, it was curved somewhat like a boomerang. The root of the penis, or the first third of the shaft, was straight, but then it turned upward by an angle of around 120 degrees. This meant that the diagonal position as drawn by Da Vinci was incorrect. The penis is much more vertical than was thought. The researchers also found that the size of the uterus does not increase during sexual arousal, against common thinking at the time. And they also discovered that vaginal sex in women prompts the bladder to rapidly fill, something that was observed in every participant. This happened despite each woman going to the toilet just before the scan. The reason for this is still unknown, perhaps a way to limit urinary tract infections post-coitus. In 1999, nearly 8 years after the first ever MRI scan of coitus taking place, the results were finally published in the British Medical Journal, one of the world's oldest medical journals. A year later, the work led to an Ig Nobel Prize for Medicine and worldwide attention, making it to this day one of the journal's most read articles. It is probably my best read publication, Sibelius said, and likely will stay that way. Note: the Ig Nobels are prizes that have been awarded each year since 1991 to celebrate unusual developments in science, with the stated aim of being to honor achievements that first make people laugh and then make them think. 2. The egg and sperm race. On a frosty day on January the 2nd, 1665, the famous English diarist Samuel Pepys visits his bookseller. As he enters the shop in St. Paul's Churchyard in the centre of London, a newly released book catches his eye. Titled Micrographia, the 246-page tome contains over 40 beautifully detailed sketches of everyday objects such as a fly, flea, needle, piece of coal, as well as other bits and pieces. Rather than these familiar objects appearing as we see them with the naked eye, they look totally unfamiliar and strange, the drawings featuring mesmerizing aspects that had never been seen before. The flea, for example, is described as having a polished suit of sable black armor, together with multitudes of sharp pins that are shaped almost like a porcupine's quills. As Pepys glimpses this most excellent piece, he writes in his diary that night that the book was so pretty he could not resist purchasing a copy. When it arrives 3 weeks later, he takes it home and devours the contents in his chamber until the early hours of the morning. The most ingenious book that ever I read in my life, he notes on January 21st, 1665. The intricate drawings in Micrographia were made possible thanks to a new and powerful contraption, the microscope, that was about to lift the lid on this never-before-seen world. The author of Micrographia was the renowned English physicist Robert Hooke. He had spent several years prior to the book's publication designing and perfecting his own microscopes that used 3 convex lenses to produce a magnified image of an object. Hooke was a remarkable yet controversial scientist who made breakthroughs in several fields throughout his life, including mechanics, astronomy, and optics. At just 27 years old, he was appointed curator of experiments at the then newly founded Royal Society, the still prominent National Academy of Sciences in the United Kingdom. 3 years later, he published his observations in Micrographia, which became the world's first fully illustrated book of microscopy. The work quickly captured the imagination and had an impact far beyond Hooke's home country. Someone equally captivated as Pepys was the Dutch businessman and scientist Antony van Leeuwenhoek. He came from a family of beer brewers, but turned his skills toward his father's side's tradition of basket making, and at age 16 began working in a textile store. 6 years later, in 1654, he bought his own shop in the city. In 1668, while in his mid-30s, Van Leeuwenhoek travelled to England, where it is thought he came across a copy of Micrographia. He was intrigued with how the microscope could help him investigate the quality of different yarns for his business. After all, Micrographia contained details and drawings of various threads, including silk. Inspired by the work, Van Leeuwenhoek began to construct his own microscopes, which were seemingly simple but incredibly powerful instruments. One of his microscopes included a single lens, a tiny drop of glass about 5 millimeters in diameter, about 1/5 of an inch, mounted in a thin piece of metal like a small magnifying glass. Throughout his lifetime, Van Leeuwenhoek created about 500 microscopes, the best of which were capable of magnifying objects by a factor of about 250, 5 times the magnifying power of about 50 that others, including Hooke, could achieve at the time. Van Leeuwenhoek never documented how he produced such instruments. Some say this was because of his lack of formal training as a scientist, while others claim that it might have been a deliberate ploy to stop rivals from copying his techniques. Yet, Van Leeuwenhoek was so ahead of the game that it took over 100 years before lenses of a similar quality could be reproduced. Using the most powerful of his lenses, Van Leeuwenhoek could see items as small as around 2 micrometers, which means he was able to resolve red blood cells that are between 6 to 8 micrometers in diameter. A micrometer being 0.000001 meters, also written in scientific notation as 1 × 10⁶ meters. He was also curious enough to investigate samples from his mouth and armpits. When he studied them, he discovered something mind-boggling. They were teeming with tiny organisms that moved around, which he called animalcules. Then one day in 1677, in one small ejaculation for man, one giant squirt for mankind, Van Leeuwenhoek put his own semen in the spotlight. Note: the original use of the term animalcule is thought to have been made by Johann Hamm, a Leiden medical student in 1677. Note: it was actually Hamm who was the first to see sperm, having analyzed the semen of a man suffering from gonorrhea. See Hutzager H.L., Anthony van Leeuwenhoek, European Journal of Obstetrics and Gynecology and Reproductive Biology 15, No. 3, 1983, pages 199 to 203. Remarkably, Van Leeuwenhoek also measured the length of a human sperm to be around 50 micrometers long, resolving its head, which he found to be about 5 micrometers, or roughly 1/10 of the length of the sperm. Note: male fruit flies have the biggest sperm on record, measuring a whopping 6 centimeters, or 20 times their body length when uncoiled. Through his research, Van Leeuwenhoek not only lifted the veil on the microscopic world, as Hooke did, but also invented the field of microbiology. The 1670s marked an extraordinary decade of discovery for reproductive science, with scientists finding that female mammals produce egg cells. Despite being the largest single cell in the human body at 0.1 millimeters, possible to see with the naked eye, a human egg was not actually directly observed until 1827. For some, the discovery of sperm cemented the theory perpetuated by the Greek polymath Aristotle in the 4th century BC that the female provided the matter for the baby via the menstrual blood, while the male's semen gave that matter form. This became known as the spermist view, while an alternative ovist position argued that humans were formed from eggs, with the sperm or semen providing some sort of a waking force to kickstart development. Dutch microscopist Nicolaas Hartsucker, Van Leeuwenhoek's contemporary, was firmly in the spermist camp. In 1694, Hartsucker drew a now iconic image, a homunculus, or the complete body of a tiny baby, held inside the head of a sperm waiting to pop out and grow in the uterus. Hartsucker's sketch became a classic example of the so-called preformationist theory of human development, in which people came preformed from the very beginning of conception. This theory did not get overturned until the 19th century with the advent of cell biology and genetics. We now know that, despite being incredibly different in size, both the sperm and egg each contain half the genetic material needed to create a human. Yet, there is one key detail that differentiates sperm cells from egg cells, an aspect that Van Leeuwenhoek spotted way back in the late 1600s, their ability to swim. Sperm is an animalcule which mostly has the aspect that when living and moving, it swims with its head or front part in my direction. Van Leeuwenhoek wrote to the Royal Society about his first observations of sperm. The tail, which when swimming, it lashes like a snake-like movement, like eels in water. While we now know that sperm must travel through the female reproductive tract to fertilize the egg, it took another 250 years after Van Leeuwenhoek before anyone could offer an explanation about how they might do so. The first piece of the puzzle emerged in the mid-1900s thanks to a series of experiments that highlighted just what a strange world small organisms like sperm and eggs inhabit. Human testicles are formidable sperm factories, able to pump out about 1,500 sperm cells every second, resulting in 130 million cells every single day, or 10 trillion per year. In the time it took a man to read that last sentence, he would have already produced around...
Sample complete. Ready to continue?